Okay, so I'm Simone Bacchio. I'm a computational scientist at the Cyprus Institute. And the topic I would like to discuss in this hour is about, it's quite connected to what also Yannis presented, but it's a bit more low level. And it's about how to use C or C++ libraries from Python. And in the specific with a package named cppyy that we'll look at it today. The slides I'm going to show are available online, and you can just type in the link you see here. It will be also on the bottom of the slides. So cppyy 24, it's the name. Okay. A brief overview of the presentation. I will start with some basic knowledge on C++ libraries and how they work. Understand how these can be integrated within Python, and then we will see specific examples using this package that is named cppyy. I hope most of you are not aware of it, and yeah, you will be surprised by its powerful. So let's go and let's start a bit with this. So the main motivation to do this kind of applications is basically to accelerate Python, to really use Python for high performance computing, which is the topic of today's of this series of workshops. And we want to basically take advantage of the speed of C and C++ directly from Python, avoiding all the reasons for which Python is running slow when you just execute stuff writing pure Python code. And the reason why Python runs slow is because, okay, we all know that Python is an interpreted language. So interpret means that everything it gets executed goes through a long process before actually being executed, which is a very big difference, for instance, with compiled application, with something you would write in C or C++, because in that case, once you compile it, the compiler transforms your code in a machine code that then is executed instantaneously, and just operation are executed and nothing else is computed. Here instead, when you type instructions, these are then interpreted, and a long time passes before you get actually the result out. So so the idea here is to use Python as a user interface where you have very powerful APIs like the one offered by NumPy, SciPy, etc., but then using under the hood a compiled library. And this is what all these packages are doing, and also what actually, for instance, MPI4Py that Yannis showed today was doing under the hood. They didn't rewrote all the MPI standard from scratch, but they are linked to a library and they're going to use it directly from Python. So we want to use these. We want to use now different various libraries, and especially those that you may be of interest for your project. And so now we will focus on this kind of library that, for instance, are named dynamic libraries. So when you take a C code, I believe most of you are familiar with C, how this works. You write some C code, you run a compiler, the compiler will produce a file that is named .o. So this is an object file that it's compiled. Then these files can be either included directly in an executable or can be included in a library. And when you create a library, there are two kinds of libraries, either static or dynamic. And the difference between the two is that a dynamical library is linked at the execution time, and so objects are loaded at execution time and executed, while a static library is put inside the executable directly at compilation time, and it belongs to it. So we can understand that for Python, we are very interested in dynamic linking because as we are executing our program at need, we can load a library, link it, and then execute functions that belong to this library. And this is what all these packages are doing. If you're interested a bit about the C API behind this, you could look at this package. But this is something that Python is doing for us already, so we don't have to look at it. To understand a bit better why dynamic libraries are very important, and also how frequent they are, because basically everything you use in your computer is based on dynamic libraries. So these, if you take your terminal, let's say these are those that are stored in, for instance, user lib. Here you find all the dynamic libraries, those ending with .so, that different executable might be using. So these dynamic library are used everywhere, and all of these can be used also from Python, as we will see today. And the reason why these are so so important is because, first of all, they allow you to for a use space saving in your hard drive. This is because the functions and objects are not directly included in the executable, but main executable are pointing to the same library. Then they allow also for something for version control of the library, because once, if you have an updated version of a library, suppose you want to patch a bug or something similar, you don't have to recompile all the executable depending on it, but you just need to recompile the library, get a new version. Like here you can see, for instance, these are version 2.0 of something, and then all the packages will point directly to the latest version of the library without need to recompiling. This also means that you have a faster initialization, because the executable are they are not very large in size, and so they can be they start very fast, but then at execution time they might be loading the objects at need. This, on the other hand, may produce some issues in HPC, because having like you saw before, with, for instance, with MPI, you are instantiating many instances of the same executable running in parallel. And if all of them are trying to load the library at the same time, this produces some slowdown, but this is something actually minimal. And additionally, another thing you should avoid is to put in a shared library some security features of your package, because a shared library is highly vulnerable. And I will show you an example of this in the next slide when we go deeper into it. So let's understand a bit better how this works, and let's have some practical example. Now, we stay on the terminal side, and let's look a bit. We saw how frequent shared library are. Just a second, I need to move this. And these are used by most of the packages. So for instance, if you want to look at what certain executable, what shared library a certain executable is using, we can type LDD. Let's take the executable ls, that is the one that lists the file inside a directory. And LDD executable will tell you the list of libraries that this executable is going to use. Okay, so this is an example of dependencies. If we take, for instance, LDD of Python, let me find. So I take the LDD of the executable of Python. This you can see that there's a minimal list of libraries that is loading that has dependencies on. But then at the execution time, when, for instance, we import NumPy will add to this list of libraries other dependencies that are the compiled versions of the NumPy functions. We will talk a bit more about that. So these are the dependencies. If you want, for instance, to know where these libraries are found, you can see that a package of an executable is just listing the libraries that wants to load by their name. And then we see here how they get resolved. So this is the resolution that your system is doing. And this is where, for instance, they can be replaced. So if you change the directory of the version, the same library that the executable is looking for may point to a different one. So the resolution of the library is controlled by the, at least in Linux, by the variable LD library path. So these lists the directories where the libraries can be found. These are additional local directories you can add. You find then the default system directories that are here. Now, let's look at an example of a code that gets compiled as a shared library. And you can take this piece of code on the right. Okay, I have it ready here. So we have this piece of C code that we are going now to use for understanding a bit the vulnerability of these of the shared libraries. And in this piece of C code, I am, for instance, defining a new function that is named malloc that we are going to use now. So suppose that we take a, you have some C code and you want to compile it as a shared library. To do so, you use the standard compiler, and you say that the file should be compiled as shared. And you need also the flag fpic for using, you also need this flag. And then you can compile the, for instance, here, this executable, this file named my malloc. And we compile it in my malloc.so. Okay. And this will create a file that is a shared library that then we can use. If you're interested, for instance, in seeing what kind of functions are available in a shared library, you can use the command. You can use this readelf, because it's named readelf because elf is the standard used by the shared library and in Linux, and this will read the header. So, oh, sorry. Okay, we can read the library. And for instance, we find that an object that is present in here in this library is indeed this function malloc. And in the same way, many other are present, but are not of our interest. So those are included automatically. And now let's show you, for instance, a trick you can use with this function. That is in C, for instance, you can use the command preload, LD preload, to preload a library before executing before launching an executable. So this preloading will basically load in advance the functions included in a library. For instance, in this one, there is this function malloc. And once the library will look for the function malloc, will end up using the function malloc we have defined here, and not the one defined by the standard lib. So you can see that the standard function malloc, if is included in libc.so. So this is where you find all the C functions included, okay, defined. And what we are going to do now, by preloading a library, we are actually loading the objects inside the library before, and then we launch the executable. What is this going to do? So let's see the first example, and then we discuss it. So if I say LD preload malloc, yeah, you cannot see it here, just a second. I move it higher. So if I say L3 preload malloc, what happened here is that I've loaded first my library before launching the executable, where I've defined a new version of the function malloc. And this, what I did in this piece of code here is basically every time the function malloc is called is to print. So this is the standard signature of the function malloc. This returns a void, a pointer to a piece of memory that gets allocated and gets as an argument the size that we want to allocate. So this is the standard definition of the function. And what I'm doing here, for instance, is every time this gets called, is to print the size of the piece of memory that we want to allocate, and then print also the pointer that gets allocated, okay? So this is a function that will, every time the malloc is called inside ls, is going to print with what argument we called it. And so you can try to understand now the vulnerability of this shared library, because what we did, we replaced with a homebrewed version of the function malloc that is going to tell us all the property of it, okay? So something very similar could be if you have a package that wants a password or something, a login to, let's say, an approval for executing some part of the code. And if you replace, if the approval function belongs to a shared library, you could easily replace it with your version of the function that says, yes, the password is correct. So suppose it turns true, a function that is named, is this the password, let's say. We return true automatically, and this will bypass easily all the control that your package will do. But this is just an idea of this, how these things work. So you're basically loading a piece of code defined in a library that then gets executed by your what you precompiled. Okay. Is there any question on this side? So, and online also? Okay. So let's try to see a bit now how this can be done the same in Python. So the idea now is to do something very similar in Python. We're executing Python code, and we want to load at runtime in Python a function that got compiled in order to use directly C code inside Python, okay? And how do we do this? We are going to do this using cppyy. But first, let's understand how this is done under the hood by most of the things. And let's take as an example NumPy, okay? So everything that you are running in Python is actually executing functions under the hood that have been precompiled And to understand this better, we are now going to move to the Jupyter notebook that you can access by using this URL here, okay? So it's the same URL as before, we then be at the end. And we are going to see how this is done on the Python side. So let's start understanding a bit how this works. Let's take, for instance, NumPy. What NumPy does, if you want to, NumPy, you all know NumPy. NumPy is this Python module that allows you to perform very fast manipulation of array of data, okay? And data is very flexible. And what is NumPy doing? NumPy is creating, for instance, arrays containing information, let's say numbers. And what will it do? We store them in memory. Now, in order to be able to perform fast mathematics, NumPy has to do few things once you define an array. It has first to define a data type. This is very important because when you run a C code, you need to have a well-defined data type, right? So it needs to deduce from your, unless you specify it, it needs to deduce from your input the data type. You can also specify it, for instance, like this, saying data type equal float, and these now are float numbers, right? Otherwise, we deduce it from your input. Those were all integer, the data was integer, okay? It defines a data type and also a size of it. That in this case is the shape, but actually the NumPy also works with sizes. And the array of size in this case is still 4 because it's the same of a shape. But even if the array is a multidimensional array, the size will always count the amount of elements. So once NumPy does this, so it gets a data type and a size, it can then allocate a piece of memory containing the data you have. And then this piece of memory, which results in a pointer, can be passed to functions and used by precompiled libraries. So for instance, if we take this array that we have defined, okay, and we want to find out what is the pointer of it, we can use the array interface. We can look at the variable array interface, and this variable contains all the information that NumPy needs to operate on the C side. And these informations are, for instance, the pointer, and this weird number is the pointer of the data. So are these numbers that before we saw in on a 16 basis format. Here it's on a 10 basis, but it's the same number, okay? The data type, so this is a float of size 8 bytes. Here it's float 64 because 64 stands for the number of bits, but these data are always allocated in bytes, and so this is these are 8 bytes, okay? And the shape of it, okay, this is the version of NumPy, doesn't matter. So these are the information that NumPy needs to operate, and they're all belonging to this array interface. This pointer then, you can understand, is passed down once we do an operation like array times 2, okay? What NumPy will do is to call a precompiled function in a library and pass this pointer the size of the array and say multiply by 2 all the elements. And this is all you need for operating on the C side. This is very important to know that NumPy is doing this because very often you may end up in two situations that you don't understand why they're happening, which are due to the fact that NumPy is actually never, most of the times, not creating copies of your array, but always avoiding it if possible and pointing to the same piece of memory. So for instance, if we reshape the array in a base 2 by 2, okay, what you get is that the reshaped array, the array number 2, is actually pointing to exactly the same memory, okay? And the only thing it changed between this array here and the array here is just the view of this data are still the same for numbers, just that here are seen as something that is shape 2 by 2 instead of having a shape of size 4. But are still exactly the same numbers, so NumPy is still pointing to exactly the same piece of memory. And this also happens, for instance, when you take a slide of the array. So for instance, you take a slide from 1 on. What NumPy is doing is actually still pointing to the same piece of memory. You may say, no, it's not the same. Well, it is the same because everything is equal apart the last number, okay? Which is just the pointer. This is what you will do in C. If you want to see something that starts from 1 on, is to get the pointer shifted by, in this case, you see 8 bits. So we do 4 plus 8, we got 12. This is an array that starts from the point, from the next element and has a size 3, but is still pointing exactly to the same piece of memory. Why is this important to know? Because, for instance, if I'm going to change now in the original array the first element and I set it to 0, what I get is that I see a 0 here, okay? But the same 0 is expected. But the same 0, you see it also in array 2 and in array 3. This is because these arrays were just view of the other array, starting from a different point, okay? Basically, what NumPy is doing under the hood is just using, it's just providing you the URL to collab is in the slides. It's the same as, unless it's not working, but it's the same as the URL of the slides plus NB at the end. And yes, it's pointing here, okay? And so this one, I leave it here a second to see it. Okay. And what I was saying is that, yes, what NumPy is doing is just using C under the hood and is behaving exactly like a C code. This is, for instance, also true if you define an array like before of integer. So we say this is an mp.array. I will paste the URL to the chat, just a second. I define an array of integer, let's say, okay? This is something that is a data type of that is an integer. And what will happen in C if you try to assign to a component of it a float? Let's say I assign to the component 0 the number 1.234. What is this going to happen in C? In C, what would happen is that this number, this floating number, gets casted to an integer, because integer is the data type of the array. And exactly the same happens here. NumPy is not going to change the data type of the array, but rather changing the data type of the assignment, right? So since this was an array of integers, this stays an integer, okay? And now I'm going to paste in the chat the URLs. And if you have questions, please ask right now. Yes. Sorry? I see people connected. Yeah. You have, let me put it in the, I think for the others worked. So let me put the notebook and the slides. Try, does it work? You should be able to connect to Google Slides, yeah. Sorry? Not in Zoom, if you press the link, I sent now the link on Zoom. Right? Did it work? Just a second now. Okay, so questions, other? Okay. So let's go back to we're also running out of time. So basically, Okay, if you're online, start executing this command. In the meanwhile, I told you that it takes some time to install cppyy. So I execute that. Basically, as we said, yes, NumPy is using under the hood all the time compile function in C and C++, and then just calls them by passing to them a pointer to the array and the informations on the data type. Okay, so we want to be able to do exactly the same, but with additional functions. And why does NumPy do that? Because doing operation in C and C++ is significantly much faster. So when you need to operate data, it's much better to operate them with compile code than with Python for loops. So this is what NumPy does. And like we saw, what actually does is that anything you see in this very beautiful API that NumPy provides, it's actually just a complicated view of functions that are actually implemented in C simply as view of unrolled data in any case. So when you have an array, for instance, shape of a 10-dimensional array, let's say, with many different sizes, actually when you operate on it, the data are always stored unrolled in a sequence, and NumPy simply rolls over them and does an operation. So you want to add two arrays, it just pairs them up and add them to each other, independently on the shape it has. So it performs always very fast under this point of view. And this, you need to be also careful about this, because often you have the same pointer. You're actually pointing to the same data, especially when you do slides and reshaping. Now, set this on NumPy, you understand how this is frequently done. Let's try to do it by our own by compiling some C library. And for doing so, we want to use cppyy. cppyy is this package that it offers, as it's advertised, an automatic runtime Python C++ binding. So binding is the term that is used when you want to, instead of linking in case of Python, because this is done at runtime, and in Python it's named, you're binding to a C library, the functions in Python, and then calling them. So you're not simply linking because you don't compile your code, but at runtime you're binding the functions you are going to execute and call them from C. So we use this package to execute functions. We will use this package, and more information on it, you can find it on this URL for the documentation. You install it via pip by doing pip install cppyy. And an idea of its usage is via these commands. So basically, you can either directly define some C++ code, or you can load libraries, including with the header, and then you can, anything you did here, you can then from Python call functions that belong to the library. And now we go to see all of these. And we'll do some hands-on on the notebook. Okay. So let's, I have it here. Let's move here. I hope you had run before this command. It takes a bit of time, and after 2 minutes, you get the package installed. Okay. Once you have the package installed, you can simply import cppyy. So this you can do it locally, online, doesn't make a difference. Now, let's do a very simple, basic example that every programming language does, like writing an hello world. So suppose we want to write, we have some C code that, in this case, returns a standard string, and it's a function named hello world. Okay, so this we are directly giving it to cppyy as a piece of code. This can be done either by directly including a C file, or or like this at runtime, okay? cppyy, what we'll do, we'll compile it and will tell us true because there were no errors. So it's telling us true, I've been able to compile it. You do some mistake, you don't put a semicolon at the end, it tries to compile it and will tell you, we give you the compiler error saying you missed a semicolon here. Once you have the correct code, you can compile it. It should produce the output again true, but what it's saying is that this has been already defined. This is because we already compiled this piece of code, and now we have the function was already defined. Nevertheless, it was compiled the first round, okay? So you cannot change at runtime the content of a function. Have this in mind. If you want to play with it at runtime, every time you make a change, just change the name slightly. So for instance, hello world 2, now it works. Okay, we compiled it very well. And what we can do now is to use the GBL that stands for global, okay? These are a set of global variable that has been defined. And inside the GBL, now we will find a function, hello world, okay? That is a pointer to this function that cppyy compiled. And this function, we can call it without argument because the function wasn't taking any argument. We call it and we get the output. So what cppyy did here was to compile the code, linking, bind it, and then call it via the function here. Suppose we put we pass a different string instead. Let's say we want to pass we want to define our print function. Let's say like this. We define a print function that takes a standard string. What let's name it A, and we return A. What cppyy will do now, if we call this print function, is to pass a string that we define in Python. So this is a Python string. Okay, convert it to standard string, pass it to the function. The function at this point is doing nothing special, just returning it, and we get it back. So basically, what cppyy is able to do is to convert any Python object to a C equivalent object that then gets manipulated from the C side. Okay. So this is something that cppyy does. Additionally, like we said, it works both with C and C++. So you can see here, for instance, we already use C++ by defining a standard string, but in the same way, we can use here, for instance, like in C, a pointer to a series of characters. So this is how like you would do it in C. Okay. And cppyy will know how to convert the same string either to a standard string or a char pointer independently. Okay, so it has these various functionalities. Okay, so this is very powerful. In the same way, it works with anything else you can do in C++. Suppose you have a class, a structure, etc. Let's define a structure of coordinates. And we can, for instance, initialize it now. Once we define it, we can initialize it from C. And now this object, coordinate size with 1, 2, it's you see here, it's an object that is managed by cppyy, and is pointing to a piece of memory that has been allocated, and it has this coordinate stored. Okay? And then we can access them directly from Python or even modify them. Okay, so this is then something okay, this is something that then you can use, because suppose you have a library that gets as an input of or you want to use functions from a class, you can just initialize a class that is defined in C++, pass the arguments from Python, Note this supports also naming of the variable, so I can say x equal or y equal. This is fine. Okay, it's not a problem. I could actually invert them, and shouldn't be a problem. This is something you cannot do in C, but from Python you can do them because this is named now. And you can manipulate these classes and then use any function you have in your library that you want to target in that it was written in C++ from Python and execute it at its regular speed. Okay. To give you another example, suppose you have more C++ oriented code that supports templates. This is a templated structure. So for those that don't know how template works, if you want to write a code in C++ that is agnostic on the data type, suppose, we can now define a templated structure and define a type name T. T is going to be the variable type. And this templated structure now can be, for instance, like it's the same as before, just that instead of integer, now we have a type T that we can specify afterwards. So we can define for instance, a templated structure here, initialize an integer version of it, and this is now an integer version of the structure. And the same way we can define a float version of the structure, and now inside with 1 and 2, but now are floats, and now you can see that this gets printed at 1 point and 2 point. I hope you can appreciate how powerful this is, because you can really, from Python, do anything that you will do in C++ and call libraries. Yes. This is not using Python. This is using C++ compiled code. It's compiled, not interpreting. Of course. So you directly call the library. The purpose of all of these is to give you a way from Python to very easily interface to a written, to a compiled C library and call it. Okay? So it gives you all the tools to get to pass. Basically, you need all the tools to pass inputs and get outputs from for libraries functions. So you want to call this that we called here, okay? Although we define it here at runtime, it's not interpreted, it gets compiled. So it will simply put this piece of code inside a C file, compile it as a shared library, load it, and do a bit of things. But this provides directly the compile function. And what cppyy is giving you are all the tools to pass a Python object as an argument to a function and retrieve the output of this function as a Python object. No, it's compiled here. It's compiled here. When it says true, it's because it's compiled at its definition. No, it's compiling at runtime. So when the Python code arrives to this point, when you execute this function from Python, it's going to compile it. It's not, but it's not interpreting, it's compiling. It doesn't interpret this code, it just gives it to a compiler. The execute, of course, Python is always interpreted. It's not compiling Python. I mean, the difference, for instance, with Numba, I don't know if you know Numba doesn't do something similar. Numba, what it does, it's accelerate Python code by compiling it. In that case, Numba converts a piece of Python code into a C code and compiles it. The purpose here is different. The purpose can be understood better now in the following example, where you want actually really to use a library. So it's plenty on your scientific fields of libraries that are available on GitHub, okay, that are written in C++ because it's the standard way to write it. And you just go here and you have a good library you want to use. If you compile this library as a shared library, then from Python you can load it and just execute it at the same speed. So from Python you can write a very interesting API, which is what NumPy does, or what MPI for Pi that we saw before does. MPI for Pi just wrote a Python API to a compiled MPI library. And then you just call it. Okay, so this is what everything in Python does that is HPC-wise. I mean, everything that it's based on a library does this. It calls, not via cppyy, there are other methods, but cppyy is one of the best user-friendly methods, okay? So let's do this example that is more basic. You have a library, okay? We have a library that, for instance, we name square, and this is a simple header, and it's a library that does the square of an input. It implements two versions of it, of this square. Either is something that you give a double, it gets a double, or it's something that you pass a pointer to a double array and returns in output the square of input, okay? This is a library that you can find online that, of course, for your scientific field, it might do more interesting stuff than just squaring. It might do, I don't know, suppose neural networks, some convolution or things like that you want to call it. You just arrive here and you want to load this header file. Okay, so on one side you have the header that you know. On the other, you have the C implementation, like this one, that it's a C file that we are going to compile and does what you expect. It's squaring a number, x times x, or it's squaring an array, does input times input. Okay, so these are two pieces of code that with this magic line here, we can write directly in a file, but this is an example of what you may find online, or you may use in your project, okay? This code gets compiled as a shared library, which we talked before, like we did before. We just compile it, okay? And now this ahead of time, this is not something you're doing in Python. This is an example here, but it's something you did ahead of time. Ahead of time, you compiled your library, like all the others that are available there. And you have now two objects that you're interested in, which is the header and the library. So if you have these two things for your package, okay, what you can simply do from Python side now is to use cppyy to load the library. So this is going to link dynamically at runtime to this library. We link to it. And we include the header file. By including the header file, what cppyy does is to read the content of the file, parse it, and define the functions like the way we did here, okay? Just that now, what we defined here by reading this file is not the implementation of the function, but just the signature to this function. So this is the function that it has this signature, and we are telling you need to know this because cppyy needs to know what how this function should be called and what it returns. So once, if you want to execute any of these objects that are now belonging to the shared library, you need to know what it gets as input and what it gives as output. Without knowing this, you cannot use them. So this is why it's important you must load something, because otherwise just loading the library doesn't tell you what it's in the library, okay? As we do these two pieces of codes, we have now inside our GPL a square that is this function that cppyy did not compile it because it was compiled before. It just linked to, and we are going to use through the library, okay? So we have the square function, and now we call it for 2, and this is going to return us 4 as expected because we have, this is what it does. Suppose now I change no, this cannot be done here. I need to load it again. So you cannot change at runtime neither the content of the library. But if you change the library, when you load it, if this is different, it will execute something different. Okay.
Can you unload the library and reload it with new changes?
No, no, you cannot. So if I try to load again the library, we still say true, but I don't because the object was already loaded, so it already knows where squared is placed. So suppose I compile this, I have a new version of it, I load it again. The problem is that I already have loaded square once. I already called it once, so it already linked to the object that was compiled before. So this cannot be done at runtime. But it's something you don't want to do at runtime because these are libraries you compile and then you execute. Okay, so this is not important. Nevertheless, you see, now we have executed we have compiled a library and we are calling it. What if we want now to pass an array? What is an array? What is a double pointer? Well, an array in Python, it is a NumPy array. So suppose we create now an array with 1, 2, 3, 4. We create an output. Here now we need to create an output that is empty like the array. And we want to call it. Well, cppyy now is complaining, and it's complaining correctly because the type of the array is double here, and so it cannot convert an integer array into a double pointer. If we do it properly, we define an array of double and an output that is double, you can see that now very easy we can call square n, that is this function that it's looping over the size of the array and it stores the square inside the out, okay? We loop over it, and our output now contains the square of the input, okay? And this is really, really all you need for calling from Python functions that belong to libraries. Yes, please.
Okay, but say we have like some very large piece of C++ code, then every time we run the Python code, it has to compile.
No, it's not like that exactly. You don't, because you load the library. You're loading the library. So the question was if you need to compile every time. You don't. So suppose you want to use, maybe some of you know, if you want to do some linear algebra, there are the BLAS function. If you take a BLAS function and if you take one of these implementations, you see inside, okay, this is not working, but inside some of the compiled BLAS libraries, and inside those you find implemented all the functions that are defined in the BLAS standard. So I want to give you an example, but these basically are just functions that take arrays and do operations of them. Okay, so let me find BLAS routines. Suppose here you have, if you are on a computer, some implementation of some of these routines. For instance, this is a matrix product, etc. You want to do a very fast matrix product. You load the header of the BLAS library. You include, which is named in this case mkl.age. You include the compiled version of it. And then what this gets is something just like the pointers to the array that you want to use inside this function. These are more complicated function, but if you take the level one that are the simple, let's take you want to do ax plus y, which is this routine, is something that just gets the size of the array, the pointer to the arrays of the input and output, and the scalar factor. And then you are using this very powerful library that is extremely optimized to do arrays operation. And the same, you can do it, and this is what actually NumPy does for most of the things. It uses BLAS, but nevertheless, this can be done for any library you are interested in, okay? And everything you need to do is to load the header and the library, okay? And then you find from C, you find from Python, a function that you can just call passing, in this case, NumPy arrays or passing objects that you create at runtime. Suppose you want, in this library, they define some structure, like I said before, okay? In this library, they define some structure. You can easily, from Python, create this structure, pass the values, and then give them to the function. Okay. So, this is what I wanted to tell you about this package that I use really a lot. It's powerful, and it allows you to bring efficient implementation of libraries in your Python code and use them. Okay. Have it in mind. It's very easy to use cppyy. Okay. Questions? Yeah. Maybe use the microphone because the online they don't hear you. Yeah, it's okay. No? I will repeat the question. Okay.
You already mentioned like we compete like generate by
the other way around. That's a very good question. So the question is whether the arrays can only be generated. So basically, your question actually should be, what if my function is returning a pointer to an array? Okay. And what will cppyy do? So suppose I define, now I don't have an answer to that, we need to try. But suppose I define some C code that allocates an array. Let's say something that returns a double star, and you have a function that we name foo. And this we pass here an integer that is the size. And what you will do in C is something like return malloc of size times size of double. Okay. You will do something like this in C. Here it's C++, so it doesn't like this, but I cast it to double star, let's say. Okay. And now I want to call from Python this function that I find in GBL, I name it foo, and I say a size of 10. Now, apart of this, will produce now a memory leak because this will never get freed because it's not a smart pointer, it's nothing, it's a C pointer. But let's store it in R. Okay. GBL, not GLB. Now, the question is, what is R? Well, R now, it's a low-level view to this to this pointer, okay? That I guess I can access. So if I access the component 0, I get a number that now it's random because it's we did not assign anything. Okay, so this is a random piece of memory. But if I ask for the type of R, will tell me that the type of R is this level view, but sorry, the type of val, it's this, it's a float number. Be careful though. Float in Python are double precision number. So the type float in Python is actually a double precision number. So they name it float because it's actually a double. But suppose you want to return, so it knows that this is a pointer to doubles. You get the value. You can manage it. So I can also, for instance, free it. So I can say cpp. I can simply just call cppyy.gb. By the way, you can do everything from the GBL directory. So I can call directory free of R. This will free it. Okay. You can also easily get segmentation faults by doing this, right? But suppose I want to do a malloc, I can easily do a malloc here. I didn't have to write a function. I allocate something of size 8, which is a double, Okay, I just allocate it, and this will give me a pointer. Okay, but then it doesn't know what is it. So I should use, for instance, cppyy.gbl static cast. No, .std, sorry, it's part of the standard. You see, you need to do, you have access now to all the, here it gives you help. You can have the access to the cast, static pointer cast, something like this. Anyway, you have access to the whole C++ set of functions, and those that belong to std, you find them inside std. So you really, from Python, you can call everything that's available in C++, okay? And these, well, yeah, now a more tricky question, it would be, how can I convert this double pointer into a NumPy array? That would require some thinking, but you can do that. You basically need to pass the pointer to the NumPy array. You can create a NumPy array by pointer. If you look online, you can look how to create a NumPy array from pointer. And this, you can, NumPy allows you to do that. So if you look here, you can use this NumPy C type as array. So there are ways to do it. So NumPy gives you all the tools for doing that. Yeah, this is the function, you see. So if you want, if you have a data pointer, you can use this function to give a data pointer a certain size, and this gives you an NumPy array. So that's then a view of the data pointer that you allocated. So if you have a library that returns a double pointer to whatever, you get it like this, and then have in mind that you need to free it afterwards, right? But I used it so far, I didn't find anything that stopped me to do everything I wanted. You just need to look for it, okay? Other questions?
Compared to C Python, is this faster? Because you can compile Python to C using
I
the
know,
C.
it's much more productive and easier, because when you want to do the bindings in the standard way using Cython, not CPython, because CPython is the compiled version, you want Cython. For instance, using Cython, I don't know if you ever tried to do that, it's extremely awful, because you need to manually write in Python the bindings, and it's not as simple as loading the header. So when you want to use, for instance, Cython, well, I mean, you should, we can discuss it further, but if you look to Cython, you can, what you need to find is to manually write all the linking. This is, for instance, what is done in MPI4Py. So if you take MPI4Py, you go to the GitHub page, and it was already there anyway. Yeah. You see, also MPI4Py, the package used before, it's named Python bindings to MPI. And what they had to do in order to do it, to link to the standard library, is to define in here all the header files that in these files here, you see these pyi is where they define all the include types. So here are defining all the functions that are available in the library, saying what arguments they take and what is the output. So basically, manually, if you wanted to do it with this way, you had to manually define all the functions, which is extremely awful. The advantage of cppyy is that everything you have to do is to include the header. By including the header, cppyy will automatically generate something like this, okay? Which is a conversion table from Python object to C objects. So
Okay, thank you.
Okay. And about speed, it's very fast. It's very, very fast. It doesn't have performance issues. Okay. Okay. I think we are done, and also within time. So I leave then the word to Nikos.